Hi there, I'm Micaela Kaplan, the ML Evangelist at HumanSignal, and this is In the Loop, the series where we help you stay in the loop with all things data science and AI. This week, we're going to look at why reinforcement learning is so popular in the robotics field. Let's get started. In the world of robotics, you have some robot, or agent, interacting with an environment. Depending on the robot, you'll have different ways of doing that. Maybe you need a car to stay on track, or maybe you need to pick something up and put it down in a different place. The way reinforcement learning works is that it provides rewards and penalties to the agent for taking different actions. The agent is incentivized to earn more rewards while minimizing penalties. The question is, how exactly do we give robots rewards and penalties? The answer has to do with the math that goes on behind the scenes. At every step in time, t, the robot has a decision to make. What action should I take? Every action has a positive or negative reward associated with it from the environment, with optimal actions, like picking up a target object or moving towards the target, receiving positive points, and bad actions, like bumping into a wall or getting close to the barrier, receiving negative points. The robot's plan is simple. Try to achieve the goal while getting as many points as possible. For each time step t, the robot will take a step that it has learned will give it the most points in the whole challenge, which might sometimes mean taking negative points. In reinforcement learning, this method of choosing an action is called a policy, and it's essentially a probability distribution over all possible actions given the current state. This is often formulated as a Markov process. We'll get into Markov models next time. Let's take an example of a robot moving through a maze. The goal is for the robot to get to the finish line while avoiding the dangerous spots along the way. At the beginning, the robot doesn't know the course at all and will more or less randomly take actions, moving in some direction or another. After every action, the robot will be rewarded or punished appropriately. Based on this feedback, the robot will adjust its behavior to maximize the cumulative reward. In other words, the path that gets the most points overall. In future attempts, the robot will know more and more about the optimal path. We can look at a similar example from Beldung. You can click on the link on the screen to see the original post, which works through the mathematical definitions of this problem. Just like before, we have a robot moving through some space, but in this case, the robot is hungry. The robot will receive a reward based on the fruit that it eats. In this case, the state of the robot is its position on the board, defined as s sub t of x and y, and s sub 0, 1, 1. In this example, the action space, or set of all possible actions the robot can take, contains 4 possible movements: up, down, left, and right. Now, we can create a probability matrix that contains all of the pairwise combinations of states, s and s prime, for all actions A. This matrix has a Bernoulli distribution, which basically means that we're looking at the probability that a binary choice happens. Either we'll move in the direction or we won't. On the screen, you can see an example of what part of this matrix would look like as expressed as a mathematical formula. The probability of going down from state 1, 1 to state 1, 2 is 1, because that's the only way to get from 1, 1 to 1, 2. The probability of going down from 1, 1 to 1, 3 is 0, because you can't get from 1, 1 to 1, 3 by moving down, and in fact, they're not connected at all, and so on and so forth. Next, we will define a reward function R. This is how the robot actually takes actions. For this example, we will say that if the robot goes to an empty cell, it will receive a punishment score of -1, because it's getting hungrier. And if it lands on the pear, it will get a score of +5, and if it lands on the apple, it will get a score of +10. Each episode, or simulation, runs for an arbitrary but finite amount of time, and it ends if the robot reaches a piece of fruit. Now, it's time for the robot to try to resolve its hunger. In practice, this learning would happen experimentally, but let's imagine what it would look like in theory. Let's consider 2 of the possible policies that the robot can choose from. If we simplify a little bit, we can think of the policy as a series of actions that the robot will take starting from state 0. In policy 1, we have down, right, right to the pear, and in policy 2, we have right, 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 down, down, down to the apple. Next, we'll compute the utility function for each of the policies. This utility function is the sum of the rewards and punishments that the robot will receive on each path. For policy 1, that's -1, -1 plus 5 gives us a total of +3. And in policy 2, that's -1, -1, -1, -1, -1 plus 10 equals +5. Now, it's clear that policy 2 will result in more rewards for the robot, so it will choose policy 2. With reinforcement learning, we can help robots and other agents learn to maximize doing beneficial things while minimizing the number of bad actions that will occur. There are many variations of reinforcement learning, such as reinforcement learning with human feedback and reinforcement learning with verifiable rewards, but they all hinge on the same principles we covered today. Tune in next time when we'll cover Markov models, which are the underlying foundation of reinforcement learning. That's all for this week. Thanks for staying in the loop. Want even more In the Loop? Check out our other videos. Don't forget to like and subscribe to stay in the loop.